All right, let's jump right in. Think about the device you're watching this on right now, or the car you drive. Heck, the entire future of green energy. They all have something in common, a set of materials you've probably never even heard of. They aren't exactly household names, but trust me, they are the secret ingredients powering our entire modern world. So let's dive into the fascinating and, yeah, surprisingly complex world of rare earth elements. So what do a smartphone, an electric vehicle, and a massive wind turbine have in common? I mean, at first glance, not a whole lot, right? But technologically, they're practically cousins. They all share a secret ingredient that makes them work. Any guesses? Well, the answer is they all depend on a mysterious group of 17 elements. We call them the rare earths, and honestly, they are the true unsung heroes of the 21st century. Okay, but here's the very first thing you need to get your head around. The name rare earth is frankly one of the biggest misnomers in all of science. The problem isn't that they're rare. The real problem is that they are just incredibly difficult to get your hands on. So this totally flips the script on what we think of as rare, right? The myth is that they're like gold or platinum, geologically scarce. But the reality? They're actually pretty abundant. Some are as common in the Earth's crust as copper or zinc. No, the real scarcity, the true bottleneck, isn't in finding them. It's the absolutely immense chemical challenge of prying them apart from each other. So what are these things exactly? Well, technically, we're talking about a group of 17 chemically similar metals. You've got the 15 lanthanides plus scandium and yttrium. But look, here's what you really need to know. Their superpower, the thing that makes them so special, comes from their unique atomic structure. Deep inside the atom, they have these shielded electrons, and that gives them these incredibly powerful magnetic and optical properties. That is the magic ingredient that engineers are desperate for. Okay, so if they're not geologically rare, then where are they? Well, that brings us to the next piece of this puzzle. They're what we call the dispersed elements. Here's a good way to think about it. Imagine you're looking for a vein of gold. It's concentrated, it's right there. Now, with rare earths, it's more like trying to collect sugar that's been sprinkled thinly across an entire beach. They're found all over the Earth's crust, but they're almost never in these nice, concentrated, easy-to-mine veins. They are, quite literally, everywhere and nowhere at the same time. Now, this is absolutely critical to understand. Not all rare earths are created equal. Not even close. We split them into two main families, the lights and the heavies. The light ones, like neodymium, they're more abundant and they give magnets their raw power. But the heavy rare earths, like dysprosium, that's the secret sauce. They're way less common and they give magnets the crucial ability to resist heat, which is absolutely essential if you want a high-performance EV motor or a wind turbine to not, melt. This distinction, it changes everything. So where do we actually find concentrations high enough to bother mining? Well, the lights typically come from hard rock minerals, things like bastnasite and monazite. The heavies, you can find some in a mineral called xenotime, but the real prize, the most important source for those critical heavy elements, is something completely different. These unique ion adsorption clays. They're formed over millions of years as rain just slowly weathers away at granite. All right, so you found the right minerals. Awesome. But that's just the beginning. Now you face the real challenge, the true heart of the problem. Separating them is like trying to solve chemistry's hardest puzzle. I love this analogy because it just captures the challenge perfectly. Imagine trying to separate 17 nearly identical twins, all wearing the same clothes, from a massive crowd. I mean, where would you even begin? That's what chemists are up against. And there's a scientific reason for this, of course. It's a phenomenon called the lanthanide contraction. Basically, as you move across the periodic table through this group, each element gets just a tiny bit smaller than the one before it. And the result? They become chemical lookalikes. They behave almost identically during processing, which makes trying to pull them apart with standard methods, well, nearly impossible. I mean, the journey from a piece of rock to a pure element is just epic. First, you have to mine enormous amounts of ore. Then you crush and grind all that rock just to concentrate the tiny bits of mineral you actually want. Next, you dissolve that concentrate in some seriously powerful acids. And only after all of that can the real work even begin. This incredibly complex, multi-stage separation process called solvent extraction. And just how complex are we talking? Get this. To separate just one rare earth element from its siblings and get it to high purity can take over 200 successive purification stages. 200. I want you to picture a massive factory, just a labyrinth of pipes and tanks and vats, all of it designed for the sole purpose of telling these chemical twins apart. It's wild. So, this immense technical challenge, it has profound real-world consequences. And that brings us to the global supply chain. Because it's simple, really. Whoever masters this incredibly complex chemistry controls the entire market. You know, for a lot of the 20th century, the US was actually the world leader here, mostly because of the huge Mountain Pass mine in California. But then things started to shift, and shift dramatically. In the late 20th century, China began to rapidly develop its own massive deposits, both the light ones and those unique heavy rare earth clays. And by the early 21st century, China had established total dominance. And not just in mining, but critically in mastering that complex separation and refining process. And the result of that shift, well, it's pretty startling. Just look at these numbers. Today, an estimated 85% of all rare earth refining, that absolutely critical separation stage, happens in China. So let me say it again. The bottleneck isn't geology. It's not about who has the rocks. It's about who has the massive, complex chemical plants needed to process them. And that's the crucial point to take away from all this. This concentration, this bottleneck, it isn't geological. It's industrial. There are plenty of mines and deposits in other parts of the world. What's missing is the incredibly complex and frankly super capital-intensive separation facilities needed to turn that ore into usable elements. So, all of this begs a really big question, right? What comes next? How is the rest of the world responding to this massive concentration in the supply chain? Well, a global race to diversify is absolutely underway, and it's really happening on three main fronts. First, you've got the push for new mines, sure, but more importantly, new refineries in places like Australia, Africa, and North America. Second, there's a big move towards what's called urban mining, basically getting much better at recycling and recovering these elements from our old electronics. And third, and this might be the most exciting, is pure innovation. Scientists are racing to find new, less intensive ways to separate these things, or even better, designing tech that needs fewer of them to begin with. And that really leaves us with a pretty critical question, doesn't it? Our entire high-tech, green future, it all runs on these elements. It's all built on this foundation. So as we race towards that future, the real question is, are we ready to pay the real price? Are we willing to make the huge investments in the complex, costly, and diversified supply chains that are required to make it all a reality? That's something to think about. Thanks for tuning in.